Sigma squared is the noise variance. So Py given x has this formula as given in the slide here. And what we'll do is to assume a parameterized Gaussian prior. So on this vector x, we'll impose a Gaussian prior, which is the last equation on this slide. It's P of xi, and it's parameterized by the variance parameter gamma I. It's 1 over square root of 2 pi gamma I times e power minus xi squared divided by 2 gamma I. And gamma I is any number greater than or equal to 0. Now, if I had set these gamma i's all equal to 1, that would be saying that I'm going to impose a Gaussian prior on the entire vector x. And that leads to what is called, popularly known as least squares least length regression. And that will actually never yield a sparse solution. In fact, it will yield a dense solution because the g of x that you get corresponding to that is something like norm of x square, which is not at all a sparsity promoting prior. However, what we'll do here is we'll assume that the variance parameter gamma I is either random and unknown or deterministic and unknown. By making this gamma I a parameter of the distribution, and saying that this parameter is somehow unknown to us, and trying to not only estimate xi but also gamma I, it turns out that effectively what you're doing is to try lots and lots of different priors corresponding to each possible choice of gamma I and picking the best one. And as we will see, somewhat magically, this leads to sparse solutions. And in fact, it gives much better solutions than any of the previous methods that we have discussed so far. So in terms of a graphical model, because see, probabilistic graphical models is a topic by itself, but it allows you to visualize the interrelationships between variables and also write expressions for conditional distributions in a compact way. So the probabilistic graphical model for the set of equations I showed you in the previous slide is as given in the picture here. So you have these are called hyperparameters, gamma 1, gamma 2 up to gamma n. These are the parameters of the prior which we are imposing on x, and that's why they're called. So they're kind of parameters of the parameter. Okay, so we are actually interested in estimating the parameter x, and it has a prior distribution which is Gaussian with 0 mean and covariance matrix capital gamma, which is basically this gamma 1, gamma 2 up to gamma n written along the diagonal of a matrix. So that is capital gamma is a diagonal matrix, and it contains gamma 1, gamma 2 up to gamma n along the diagonal. And these parameters gamma 1, gamma 2 up to gamma n are themselves also potentially random variables. And so you have one instantiation of gamma 1 to gamma n drawn from some distribution, and each of those gammas induce an instantiation of x1, x2 up to xn. And then these x1, x2 up to xn induce a distribution on y1, y2 up to ym, because y is related to x via y equal to phi x plus noise. And you can also represent it as a Markov chain, which is gamma is leading to x, which is leading to y. And the advantage of using this kind of a parameterized Gaussian prior is that parameterized by gamma, p of x is a Gaussian distribution, which in turn leads to algorithms for which you can solve for x in a very neat way. Also, given gamma, p of x given y is Gaussian, because this conditional distribution, because y, see, if p of x has a Gaussian prior, look at this equation here, y equal to phi x plus v. X is Gaussian because p of x gamma is Gaussian. So if you're given gamma, p of x is Gaussian, v is Gaussian, so noise is Gaussian. So y is actually a linear combination of two Gaussian vectors, and so y is also Gaussian. And so are these conditional distributions, p of x given y or p of y given x. All of those are Gaussian. So everything is Gaussian here. And since p of x given y gamma is Gaussian, it's easy to find point estimates. Or for example, you can just write out the minimum mean squared error estimator. It's just the conditional mean or the mean of this distribution p of x given y comma gamma. However, we don't know gamma. I mean, that's the whole point here, that we started out by saying that gamma is an unknown hyperparameter of the distribution. And so when we don't know it, we have to approximate or estimate it. So instead of using P of x given y parameterized by gamma, we will use P of x given y parameterized by gamma hat, where gamma hat is some estimate of gamma. How do we estimate gamma? We can use a maximum likelihood estimation approach, which is to say gamma hat is the argument gamma that maximizes the probability of, or the probability density function of gamma given y. This is what is known as the maximum likelihood estimate of gamma. And like I mentioned, there are two possibilities. One can consider gamma to be deterministic and unknown, or random with its own hyperprior distribution. The algorithms you end up with are actually quite similar, except there will be some correction term if you have modeled it as random with another hyperprior distribution. I will focus on the deterministic and unknown case in this talk, but just keep in mind that the other case is also very easy to handle. It's something very similar. But once we've estimated gamma, so I'm not talking about how to estimate gamma yet. I'll come to that a bit later. But once we've estimated gamma, like I mentioned, P of x given y gamma hat is a Gaussian distribution. In fact, we can write out exactly what that distribution is. It is a Gaussian with mean mu x and covariance matrix sigma x, where this mu x has this formula given here, gamma hat phi transpose times phi gamma hat phi transpose plus lambda times the identity matrix inverse times y. And sigma x has another big formula here. But the point here is not to be bogged down by these scary looking formulas, but rather to know that these things can be worked out quite nicely. And so you can actually write out what mu x and sigma x are. And for example, if you're interested in the conditional mean estimate, which will also minimize the mean squared error, if gamma hat were the correct estimate of gamma, so this is the MMSE estimate of x, and therefore you can expect it to have good mean squared error properties. And you can use the conditional mean, which is actually equal to this mu x as your estimate of the sparse vector x. Okay, so the point of this slide is to say that there is still a problem that we need to solve, which is that we need to find the posterior or the maximum likelihood estimate of gamma. But once we have the maximum likelihood estimate of gamma in hand, then finding this posterior distribution P of x given y and point estimates of x is actually very easy. Now, how do we estimate these parameters, hyperparameters? So like I mentioned, we will use maximum likelihood estimate. This is often called type 2 maximum likelihood because gamma is not a parameter of y directly. Gamma is a parameter of the distribution of x, and y is stochastically related to x. And so this is called type 2 estimate. So it's like you're trying to estimate the parameters of a parameter of a distribution. Okay, so the distribution of y is Gaussian with mean phi times x and covariance sigma squared times the identity. But x, so x is the parameter of the distribution of y, but x itself is Gaussian with mean 0 and variance gamma, covariance matrix capital gamma. And so when you're trying to estimate or find the maximum likelihood estimate of y, of gamma from y, that is what is called type 2 maximum likelihood. And so what maximum likelihood estimation does is simply to try to maximize the PDF of y parameterized by gamma with respect to this parameter gamma. Instead of maximizing the PDF of y with y parameterized by gamma, we can as well maximize the logarithm of the PDF of y parameterized by gamma. And this log of the PDF is the log. So actually, going back one slide here, y is equal to phi x plus noise. Like I mentioned, x has a Gaussian distribution with variance parameterized by gamma, and v also has a Gaussian distribution, and therefore y also has a Gaussian distribution. The mean of y is phi times the mean of x plus the mean of the noise. The mean of x is 0 because x is as mentioned here, it's Gaussian with zero mean and covariance matrix gamma. And the mean of V is also zero because it's Gaussian with zero mean. So the mean of Y is zero. The covariance of Y is just going to be the expected value of Y transpose, which is the expected value of phi X transpose phi transpose plus phi X, expected value of phi X V transpose plus expected value of V X transpose phi transpose plus expected value of V transpose. I'm just multiplying this quadratic. If you do Y transpose, that's the same as phi X plus V times phi X plus V transpose, and I'm just expanding that out. And that is simply this quantity here, which you see is written as sigma Y. It is sigma squared times the identity matrix plus phi gamma phi transpose. So the distribution of Y conditioned on or parameterized by gamma is actually known. And it is this PDF. And so in finding the maximum likelihood estimate of gamma, what you want to do is to maximize this log of the PDF of Y parameterized by gamma. And if I write this matrix sigma squared I plus phi gamma phi transpose as sigma Y, then this L of gamma, which is log P of Y parameterized by gamma, is proportional to, remember that the PDF of Y will have a determinant of this covariance matrix. So you will get a negative log determinant of sigma Y, plus there will be a quadratic term in the exponent. When I take the log, I'll get that as minus Y transpose sigma Y inverse times Y. So this is the cost function that I need to maximize in order to find the estimate of gamma. However, notice that gamma is sitting inside this sigma Y. So this is not easy to optimize directly. But nonetheless, you want to find the gamma that maximizes this cost function. And one way to conveniently do that optimization is through an algorithm known as expectation maximization. To do that, what you do is to look at the log likelihood of the complete data, which is Y and X. Okay, so if I look at the joint distribution of Y and X parameterized by gamma, that splits as two terms. The first term coming from the fact that Y is Gaussian conditioned on X. So its negative log is just going to be proportional to the norm of Y minus phi X squared over 2 sigma squared. That's the red term here. Plus the blue term, which comes from the prior distribution on X, which is the Gaussian distribution. And that gives us 1/2 of summation of xi squared over gamma I plus log gamma I. And using this complete data's log likelihood, you can actually do this EM algorithm, where it consists of two steps. One is known as the E step, which computes what is known as the Q function. If you haven't seen the EM algorithm before, then I recommend looking at Bishop's textbook on pattern recognition and machine learning. It's a very, very nice book, and it has, I think, a whole section on the expectation maximization algorithm, which is very beautifully explained there. And you can look it up. It's not difficult to follow. It's a short little section that you can go through. But the EM algorithm consists of two steps, the E step and the M step. And in the E step, we compute this Q function, which is the expected value of the expectation over the distribution of X given Y parameterized by the previous iterate of gamma, which is written as gamma of T, of this negative log of the joint distribution Pyx parameterized by gamma. And that, because negative log Pyx parameterized by gamma has the form shown in the first line, that can be directly written out to be in this form. It is expected value of xi squared given Y parameterized by gamma of T divided by gamma I plus log gamma I. So it has a simple form. This expected value of xi squared given Y and gamma of T actually follows from this formula here, which is this mu x as written in this slide. That is exactly, or actually the trace of the sigma x written in this slide. So that is just that expectation of xi squared. So the sum of the expectation of xi squared. So this is also easy to compute. Okay, and now once you found this Q function, the M step maximizes this Q function with respect to these gamma i's. Now, when I look at this Q of gamma bar gamma of t as a function of gamma I, notice that each gamma I appears in only one term of the summation, and it is of the form 1 over or some constant over gamma I plus log gamma I. So maximizing that with respect to gamma I is super easy. You simply differentiate it with respect to gamma I and set it equal to 0 and solve, and you will get a closed form solution. And that M step is given by, the closed form solution is given by the diagonal matrix consisting of mu I squared plus sigma II as its diagonal entries. And this mu I and sigma II are the ith entry of mu and the I comma ith entry of the matrix sigma, which are written in the second line in red and blue. Sigma is this matrix, sigma to the minus 2 times phi transpose phi plus gamma of t inverse, the whole inverse. And mu is this mean vector, which is sigma to the minus 2, capital sigma phi transpose y. And so, so the E step basically consists of computing this red and blue line, which is capital sigma and mu. And the M step consists of updating this capital gamma to gamma of t plus 1 to be equal to diagonal matrix consisting of mu I squared plus sigma II. So putting all this together, yeah, this diagonal entry is just expected value of xi squared. Okay, so given y and gamma of t. So putting all this together, we get the following algorithm. You initialize gamma to some convenient matrix, say the identity matrix, and then you compute this capital sigma and mu, and then you update your gamma. And then you just repeat these two steps 2 and 3. And once say the mu converges to something, you output that mu as your estimate of the sparse vector. So even though we went through a lot of math to arrive at the algorithm, you notice that the algorithm itself is actually quite simple. It just requires 2 steps to be iterated one after the other. So here is a small empirical example, simulation-based example to show the relative performance of some of these algorithms that we discussed so far. What I did to generate this plot was to generate a random matrix of dimension 50 cross 100. So it has 50 rows and 100 columns. And then I generate a 100 length sparse vector, which I call x0. The number of non-zero entries in this sparse vector x0 is what is plotted on the x-axis. So for example, when the x-axis value is 15, it means out of the 100 entries in x0, 15 entries randomly chosen are going to be non-zero. The remaining 85 entries will be equal to 0. Then I compute y equal to a times x0. Then I will give y and a to a recovery algorithm and ask it to solve for x0 or recover x0 for me. And I average over, say, 1,000 trials. I say that the algorithm makes an error if the error between x0 output by the algorithm and the true x0 is more than some threshold, say 10 to the minus 6. And I repeat this for different sparsity values. What is plotted in the figure is the probability of error, which is the number of times out of these 1,000 trials that the algorithm output an x0, which is more than, say, 10 to the minus 6 away from the true sparse vector x0. And the x-axis is the sparsity level, or the number of non-zero entries in x0. So the lower, the better the performance of the algorithm is. And we see that the 2 most popular recovery algorithms, L1 and orthogonal matching pursuit, that is the red and pink curves, have a performance which is kind of similar to each other, although in this case, OMP slightly outperforms L1 recovery. But sparse Bayesian learning is way down below, and in fact, it's able to achieve almost no errors up to a sparsity level of something like 18 or so. And And then it's obviously if the sparsity level goes beyond a certain point, all algorithms will start to fail. You just don't have enough number of measurements to recover the sparse vector. Okay, any questions so far? So
Yes,
this
sir.
should, yeah,
Uh,
yeah,
Sir, if, we are estimating the this parameter, the gx, in terms of mu and sigma, mu and gamma. So, or the sigma, that mean and variance. So, sir, instead of doing that, if we are doing the divergence, like Kullback-Leibler divergence or this kind of stochastic distance divergence to to maximize the to minimize the distance from the or from the estimated x and the normal x. Sir, is that any possible solution for that?
yeah. So it's an excellent question actually. So it turns out that, I mean, there's a whole theory around this also, which again, I didn't know how mathematically inclined the audience was, but that's a separate tutorial by itself. But I can talk about the mathematics that goes behind the sparse Bayesian learning in a much longer presentation by itself. But it turns out that, and I'll talk a little bit more about this later in the slides, but it turns out that this sparse Bayesian learning is a special case of a general class of algorithms you can derive through an approach known as covariance matching. And essentially what you're trying to do is to match the covariance that you're obtaining from your observations with the covariance you will get from your model. And in order to match the covariance, you need to take a notion of distance, and different notions of distances will lead to different algorithms. And sparse Bayesian learning in particular um, is the algorithm you'll arrive at if you choose a distance metric known as the Bregman log-det divergence metric. When you use that Bregman log-det divergence metric, the cost function that you eventually arrive at is exactly the sparse Bayesian learning cost function. But other divergence metrics between distributions can lead to other cost functions, and some of these other cost functions can actually lead to significantly faster algorithms than SBL and also have similar or even better performance. So it's possible to do better than SBL also by using other types of divergence metrics, or at least you can go faster than than SBL.
Thank you, sir.
Yeah. So a lot is known also about the convergence of this iterative algorithm. So one thing is, it is possible to come up with iterative algorithms for many kinds of optimization problems. But one has to ask, two or three critical questions about any iterative algorithm. One, does it converge? Two, does it converge to the right point? Three, how fast does it converge? Okay, so these are kind of three crucial questions that you need to ask. Because if the algorithm converges, but if the convergence is very slow, again, it may not be a very useful algorithm. So a lot has been analyzed about the convergence properties of this sparse Bayesian learning algorithm. And so some points about what is known is summarized in this slide. So for example, it is guaranteed to converge to a fixed point. That is, it's a fixed point is one where whatever direction you try to perturb gamma in, you'll only increase your cost function. Or in fact, a fixed point is one where if you perturb gamma from that point, for small perturbations, you won't really change the cost function L by making small perturbations. That's a fixed point. And it converges, it's guaranteed to converge to a fixed point of this, this function L that we wrote out here. L of gamma, right? This SBL cost function. It is guaranteed to converge to a fixed point of this cost function from any initialization. And it also is known that the global minimizer of the SBL cost function always occurs at the sparsest solution in the noiseless case. There could be additional global minimizers, but the sparsest solution is one of the global minimizers. This addresses an issue of what is known as a structural error in some of these algorithms. A structural error, in turn, refers to an error where the algorithm converges to the global optimum, but that's not the solution you're looking for. So, for example, when you're trying to do L1 minimization, L1 minimization is a convex optimization problem. And therefore, if you use the convex optimization toolboxes, you're guaranteed to reach the global minimum. The global minimizer is actually unique. And the solution found by these convex optimization solvers will be the global minimizer of the cost function. But that may not be the sparsest solution because your objective function, which is L1 minimization, is not going to guarantee that you'll always arrive at the sparsest solution. Whereas for the MSBL algorithm, one of the properties is that the sparsest solution is always a global minimizer of the SBL cost function. And in fact, even in the noisy case, all local minima, even if the algorithm goes to a local minimum, all these local minima will be at sparse solutions. By sparse solutions, I mean solutions where there are at most m non-zero entries, where m is the number of measurements. And it's also strictly better than map estimation under a factorial or a factorizable prior. It always has fewer local minima, and the global minimum occurs at a global optimum of the L0 minimization problem. So these are some properties of the convergence of the SBL algorithm that are known. Besides this EM-based optimization of the SBL cost function, there are other approaches also. One, for example, is known as the Mckay updates, where you take the gradient of the SBL cost function, set it equal to 0, and you solve for the variables one by one. And it turns out this actually converges faster than the EM algorithm, but it doesn't enjoy the same kind of convergence guarantees that EM algorithm offers. Another approach could be a greedy approach, where you update the hyperparameters one at a time. And if you're doing that, you can actually obtain closed form updates for each hyperparameter. This is also fast, but again, does not come with many of these other alternatives, don't come with the same kind of convergence guarantees. You can get trapped in a local minimum. There's also an approach known as fast Bayesian matching pursuit. You can go to a dual form of the cost function, SBL cost function, which is given here. And that can actually facilitate the development of iterative reweighted L1 and L2 algorithms for sparse Bayesian learning, which can be also faster than the MSBL algorithm. And this approach, being a core optimization based approach, in fact, inherits all the convergence properties of the MSBL, of the SBL, EM-SBL formulation. Okay, because this is actually at its core doing EM-SBL, except that it's going to the dual form of the cost function and then solving for X instead of using the EM-based approach. And the other one other approach is to replace the E step. If I go back here, if you look at the E step, it is this step where I'm computing sigma and mu. And notice that the computation of sigma involves a matrix inversion. So this E step is the computationally expensive step of the algorithm. So you replace that E step with an approximate posterior computation. And this leads to an algorithm known as approximate message passing sparse Bayesian learning. And this approximate message passing uses something called loopy belief propagation and Gaussian approximations. And its key advantage is that of low complexity. In particular, in the case of SBL, all PDFs are actually Gaussian. So there is no approximation happening here. It just does loopy belief propagation. And further, because the PDFs are all Gaussians, in the message passing step, you only need to exchange the means and variances, and that's what needs to be tracked through these iterations. And this allows you to replace the computationally expensive E step with the AMP-based iterations. So here is a simple empirical example where where the goal is to try to recover a 20 sparse vector of length 200 using just 100 measurements. So you have 200 unknowns, you have 100 equations, but you know that, in fact, the algorithm doesn't need to know the sparsity level, but the sparse vectors were generated to have 20 arbitrarily chosen entries to be non-zero. And what is plotted here is the normalized mean squared error in recovering this sparse vector as a function of the signal to noise ratio. And we see that the performance of this AMP-SBL is exactly matching with EM-SBL. So its performance, there's no loss in performance. But if you look at the right side plot, which shows the runtime of these algorithms, you see that there is actually 2 orders of magnitude plus reduction in the computational complexity by using the AMP-SBL approach compared to the EM-SBL approach. So it is computationally much simpler than the SBL and offers nearly exactly the same performance. So the advantages of this sparse Bayesian learning is that inherently when you're trying to estimate gamma, you're averaging over a parameterized distribution of X, but nonetheless you're averaging, so that is smoothing out a lot of the local minima. So it has much fewer local minima, and you can actually get an estimate of the error in recovery. That is the sigma y that we saw earlier. And so you can actually have some idea about how well your recovery has happened. And it's what is known as an exact inference technique, where you're exactly figuring out the posterior distribution of X and solving for the mean of that posterior distribution. It's also, it turns out, a very versatile approach, because you can use this gamma to tie several parameters together. For example, it can be used to incorporate additional structure like intra or intervector correlation, and or block sparsity or cluster sparsity. So block and cluster sparsity refers to sparsity models where the non-zero entries in the vector X occur in clusters. And you can incorporate this kind of structure into the problem by making the gammas common across different blocks. So for example, if the first 5 entries are going to be simultaneously 0 or non-zero, that kind of structure can be accounted for by making this gamma common across the first 5 entries. And that allows you to, in fact, leverage the fact that gamma is common across 5 different entries to form better estimates of gamma and improve the recovery performance. It can also be used to extend the algorithms to the case of colored noise, where in fact the covariance matrix could even be rank deficient or and unknown or partially known, etc. And so a lot of extensions are possible. And if you look at my research papers, you will find some papers on these different types of extensions of sparse Bayesian learning as well. So to recap this part of the presentation, we looked at this basic algorithm of sparse Bayesian learning, which recovers sparse vectors by estimating hyperparameters of the prior distribution. And then we looked at the expectation maximization iterations. And we discussed a bit about the convergence properties of the sparse Bayesian learning algorithm. And finally, we talked about a few alternative implementations. Now, there is no free lunch. Even sparse Bayesian learning comes with its own cost, and one of the costs is the computational complexity. And more recent algorithms like AMP-SBL overcomes this, but it doesn't exactly have the same kind of convergence guarantees as SBL does. And the other limitation is that it could be slow in its convergence, because you're trying to update these gammas, which are hyperparameters, which only loosely depend on yi's. So it's not very agile when it comes to small perturbations in y's. And there are fast versions of the algorithms, but without the same convergence guarantees. Okay, now are there any questions?
Sir, for colored noise like Rayleigh, Riccian, this kind of pink noise, the rank deficient is doing the to the Gaussian process. Sir, is it similar to the data kriging process that some kind of distribution changing?
I don't think so. I think Kriging asks a slightly different
Okay, sir.
question. It's trying to do a form of regression, but not linear regression, but regression using what are known as splines. And
Yes.
it's a different problem that it's trying to solve for. I'll have to think some more about it,
Okay,
but
sir.
I don't know if they're same.
Thank you, sir.
Yeah. Okay, so then, we'll continue on with a slightly different flavor and very important variant of the sparse recovery problem, which is known as joint sparse signal recovery. So here, the model is like this. Instead of getting one single vector y, okay, which is equal to a times x plus noise, you actually get L consecutive observations. Okay, and so you get y, which is a concatenation of vectors y1, y2 up to y capital L. And these y1, y2, etc. are all m-length vectors, which are equal to a projection of a sparse matrix X onto this measurement matrix A plus noise. Now, the structure we impose on this matrix X is that each of its columns is not only sparse, but the support or the locations of the non-zero entries is the same in each column. So, for example, in the cartoon shown here, the entries 3, 4, and 5 are non-zero in the first vector. Then 3, 4, and 5 are the entries that are non-zero in the second vector, and so on. And if a particular entry is 0 in one of the vectors, then it is 0 in all the other vectors in the same position as well. So this is called the joint sparse recovery problem. The problem is to try to recover this matrix X from the matrix of observations Y and the measurement matrix A. So in this case, the natural extension of sparsity is to say K, the sparsity level, is the number of non-zero rows in this matrix X. And depending on the problem, we may be interested in recovering X, or maybe just the support of X. That is, which entries of X are non-zero from these measurements Y. This has a wide variety of applications. For example, if you're trying to do wideband spectrum sensing, these are secondary nodes in the picture here, which are all trying to sense the spectrum. And what they do is to sample the signal over a wide frequency band of interest. And then out of the wide frequency band, only a few bands are occupied by primary users. So these secondary users are free to use other bands which are unoccupied by the primary. And in this case also, you can see that it's really not of great interest to figure out what is being transmitted in those occupied bands. The goal here is actually to figure out a few unoccupied bands that the secondary users can occupy and use for data transmission. However, notice that if you look at multiple such secondary users, the support or the locations of the frequency bins where the signal is occupied will be the same at all the users. No, it doesn't matter who is observing the RF spectrum. If there are three users who are transmitting, three primary users who are transmitting in the three green frequency bands shown in the picture, then all the secondary users will see the same three bins being occupied. And if the noises are independent, then the data that is arriving at these different secondary nodes could also be modeled as being independent of each other. And therefore, this becomes a joint sparse recovery problem. And one can try to exploit the structure that it is a jointly sparse signal as shown in this cartoon here. There's a common set of non-zero rows in this matrix X, and you can use this to improve the accuracy. It is also useful when you have multiple sensors that are observing a physical process. And these sensors acquire the physical process by using, the signals are acquired by different sensors will have overlapping subspaces, which can in turn be approximated as different linear combinations of some elementary signals. So these subspaces across different sensors overlap because of the commonality of the physical process being sensed in the overlapping sensing regions. So in order to recover this set of sparse vectors from the set of observations or sensor data, here is a generative model, which is that this set of observations S1 through SL is equal to a dictionary D times the vector X1, X2 up to XL plus noise. And the overlapping subspace in this context are the green columns here, or the span of those three columns. And so it's the column space of D sub S, where S is the index set corresponding to the non-zero entries in X, or the non-zero rows in X. So the encoder is actually linear, and you get these observations Y1 through YL, which are a low dimensional projection or a low dimensional sketch of these high dimensional vectors S1 through SL. Now I've deliberately drawn it, the S1 through SL, using multiple colors because, as we discussed, the vector X may not be sparse in the canonical basis. Instead, it may actually be sparse in a different basis. So in that case, you need to identify a dictionary matrix D under which these vectors X1 through Xk can be represented as sparse vectors. And so this suggests a two-stage decoding procedure where phi times this matrix D becomes your effective sensing measurement matrix A. So once we know phi and D, we can compute phi times D and then solve for X1 through XL. So using a joint sparse recovery algorithm, which I haven't yet discussed. And then once you've solved for XS, you just do XS, D times XS to get an estimate of this S. Now, in addition to sparse recovery, as I mentioned, support recovery is also important in certain applications. Like, for example, in wideband spectrum sensing, you don't really want to know what the primary is transmitting, but you really want to just figure out which are the frequency bands that are currently occupied by the primary user. Also, in event localization, you want an event has occurred and you want to know where that event occurred. And in this case, again, support recovery is what you use for identifying the locations where you want to put those red dots to know where the sensors are located. And similarly for subspace filtering by projecting the signal onto a common signal subspace. So before proceeding further, one basic result on the minimization of the number of non-zero rows in X subject to Y equal to phi X is that it is guaranteed that you can have a unique k-sparse solution provided k is less than some upper bound, which involves the spark of a matrix. So if you haven't heard of spark, it's not difficult, but don't worry about it. It's the smallest number of linearly dependent columns in a matrix, whereas the rank of a matrix is the largest number of linearly independent columns of the matrix. So spark is a very different beast compared to the rank of a matrix, although it looks kind of similar in the way it is defined. So spark is the smallest number of linearly dependent columns in a matrix, and rank is the maximum number of linearly independent columns in the matrix. Okay. So, but basically, when I look at spark, the spark of phi can be at most m minus 1, and the rank of y can also be at most m, And so what in turn this leads to is that this gives us a bound on the number of non-zero rows, okay, depending on the size of the matrix. Yeah, just 1 second, please. Okay, to continue, I think, it may be getting a little heavy on the detail, but the point I wanted to make in this slide is that there is a fundamental bound, which is known as the L0 bound, for this joint sparse recovery problem. And what it says is that in order to recover a k sparse, or if R of x, the number of non-zero rows in x, is equal to k, then k must be less than m, the number of rows in this matrix phi. So the bottommost line, k less than m, that is the main point of this slide, which basically puts a bound on, in other words, the number of measurements per sparse vector must be greater than the number of non-zero entries in each column of this matrix X. Okay, K should be less than M. However, if we are only interested in support recovery, it turns out that you can even recover the support, correctly even if K is greater than M. And that itself is a very large theory by itself, and it's another detailed presentation. But this L0 bound is one of the fundamental bounds on the number of measurements. So you can go down to, for example, M to be equal to K plus 1 and still recover X from Y because you have multiple measurements. Now, if you look at the support recovery performance of this MSBL algorithm, which is an extension of the sparse Bayesian learning algorithm to this joint sparse recovery framework. And you also look at the similar performance of another well-known algorithm for joint sparse recovery known as simultaneous orthogonal matching pursuit. You get these two pictures here. Now, I'll walk you through this picture. In both these graphs, what is plotted on the y-axis is the sparsity rate, k divided by n. So that is the number of non-zero entries in each column of this vector x divided by the number of entries in each column of the vector x, of the matrix x. And the x-axis is the measurement rate, which is m divided by n. And yellow indicates that the algorithm is successful or able to recover the support correctly, and red indicates that the algorithm fails. So for instance, if you take the case where m over n is small, if m over n is 0.1, it means that m is much less than n, it's only 10% of n. And if the sparsity rate k over n is, let's say, 0.5, it means that half the entries in each sparse vector are non-zero. And you can see both the algorithms are red in that regime. You cannot recover dense vectors from very few measurements. However, notice that the yellow region is much bigger for the sparse Bayesian learning algorithm compared to this simultaneous orthogonal matching pursuit algorithm. In fact, you have yellow parts which are above the k equal to m line. So it is clear that the sparse Bayesian learning based approach is able to go beyond this L0 bound, which I showed you in the previous slide. Okay, and the way it does it is actually by using the concept of correlation awareness. There is a lot of structure when I say that X is this kind of matrix with non-zero entries being occurring in the same index locations. That is, if a particular entry of X is non-zero, then all the entries in the same row of this matrix X will be non-zero. And also the prior imposed by this kind of the sparse Bayesian learning prior, which is X, each column of X, which is denoted by Xj here, is independent and identically distributed according to a Gaussian distribution with zero mean and covariance matrix capital gamma, where capital gamma is a diagonal matrix. This kind of structure in turn implicitly implies that there is zero intra-vector correlation. So if the third, fourth, and fifth entries of the first column of X are non-zero, those three entries are independent of each other and they're uncorrelated with each other. So there is a lot of structure in this matrix X that this algorithm is actually able to exploit. And that's how it's able to go so much, perform so much better than the other approaches. So now coming back to this observation model, we have Y equal to phi times X plus noise. And Y is a set of L columns, and phi is an M by N matrix, and X is an N by L matrix, which has this joint sparsity structure, and W is the noise matrix. And we want to recover X using Y and phi. Now, this correlation aware prior is one which assumes that these columns Xj, that is Xj denotes the jth column of the matrix X, these are independent and identically distributed according to Gaussian distribution with zero mean and covariance matrix capital gamma. And this capital gamma is common across all columns of X. And this enforces that all columns will have the same support. And so once you've specified the prior, you can crank through the wheels of developing an expectation maximization based solution to the ML estimation problem, which is exactly the same as before. Gamma hat is the argument that maximizes log p y given gamma, except that now y is a matrix. Earlier y was a vector, now it's a matrix because you have L observations or L vectors that you've observed, and you try to estimate a common gamma using those L observations. This is still a non-convex objective. You can solve it by the expectation maximization approach that we discussed previously. And finally, once you get the estimate of gamma, you can output the estimated support to be the support of this gamma hat. That tells you which entries of this matrix capital X are actually non-zero. And so you can go through the steps of developing the MSPL algorithm. It has the same E step and M step that I discussed earlier. The notations are a little heavier because you're dealing with matrices here, whereas we were dealing with vectors earlier. But notice that the formulas actually look very similar to what we saw before. This Q function is actually an expectation over X given Y and the previous gamma of the log of the joint likelihood or the likelihood of the complete data. And gamma k plus 1 is the argument gamma that maximizes this Q function. So in fact, the solution to the E and M steps are actually exactly the same as before, except that you will compute a sigma j and a mu j for each column, or each column of Y, that is for j going from 1 to capital L. And in the M step, you actually do a common M step across all the L columns, where you update this gamma to be the average of the individual estimates of gammas across the different measurements. So earlier, I did not have this 1 over L sigma j going from 1 to L. That part was not there. I was just updating gamma to be mu squared plus sigma, mu I squared plus sigma II. But now I update it using this formula, which actually averages the gamma across all the L measurements. So the overall structure of the algorithm and its complexity is very similar to what we had earlier, except that the M step is slightly different. And this again is a recapitulation of the support recovery phase transition of this multiple sparse Bayesian learning algorithm. And again, the point here is to note that you're able to recover the support. The yellow part is successful recovery, the green part is failure. And you're able to recover the support for k being actually greater than m. So k greater than m, meaning that these each of these columns of the matrix X has more than the number of rows of Y, that many number of non-zero entries. So this by itself is also quite surprising and almost magical that it's able to go so much beyond the k equal to m line. Okay, so we have reached the point where I explained about the um, uh, the joint sparse recovery problem. I explained about sparse Bayesian learning first, and then I explained about the joint sparse recovery problem and showed how to extend the sparse Bayesian learning algorithm to the joint sparse recovery problem. The last section of the tutorial is to discuss some applications of this in wireless communication systems in terms of channel estimation and data detection. Maybe we can take a few minutes break because we are at a 1 hour point and then come back. I'm also happy to take any questions. Okay, so maybe we come back at 3:35. Is that okay?
The performance of that MSBL, it is more than that of the greedy algorithms. But as you mentioned earlier, the complexity is higher. But still, can we go for lesser complexity algorithms in SBL to match the complexity of greedy algorithms? Whether
Yes.
it will be...
Yes, in fact, I don't know if I have those in my slides here, but let me see. I might show you some pictures. Yeah, see, this is an example of what is known as a matrix exponentiated gradient-based algorithm. This is actually a super fast algorithm, and you can see that its phase transition diagram looks very similar to what I showed you for MSBL earlier.
Okay.
And this is a far, far faster algorithm. And okay, let's see. Yeah. So you can see here that what is shown here is a comparison between three algorithms. One is known as COLASO, and second is known as this MSBL that I just presented to you. And the third is what is known as Renyi divergence-based covariance matching pursuit. And this also answers the other question I had some time back, which is, can you use other divergence measures? And this is using a Renyi divergence measure, and then it does the covariance matching pursuit. And it's based on submodular set function optimization. You can see that the recovery performance of RDCMP is very similar to MSBL. The amount of yellow you see in both the plots, the middle plot and the right plot is very similar. But if you go down in the bottom right, what is shown is the average runtime of these different algorithms. I don't know if it doesn't show the slide because I had not planned to present it. Okay, but doesn't matter. And what you can see here is that the MSBL and COLASO, see, COLASO is faster than MSBL. It's almost 2 orders of magnitude faster than MSBL, but RDCMP is even faster than COLASO. And in fact, you cannot run COLASO beyond about vectors of length of about 10,000. The MATLAB runs out of memory. Whereas with RDCMP, you can even do sparse recovery with million dimensional vectors, and it will run in a matter of a few hundred seconds.
Okay.
So it's far, far faster. In fact, to my knowledge, this is still the fastest MMV solver that you can find.
Okay.
So there are algorithms that are way faster than MSBL, but it's basically the MSBL was one of the early algorithms that showed that performance far beyond what is promised by these greedy algorithms and L1 recovery or L1, L2 type recovery algorithms can offer.
Excuse me,
Okay.
sir. You told joint sparse algorithm that is used in spectrum sensing.
Hmm.
Can you explain that, please, sir? So I'm not able to observe.
Yeah. So let me go to try to locate that slide. Okay. Yeah. So yeah, okay. I think I didn't explain this very well. So there is another one more step that I probably missed here. So when it comes to spectrum sensing, uh, distributed spectrum sensing or cooperative spectrum sensing is one of the popular approaches because of what is known as the hidden terminal problem. So basically, there are a bunch of primaries that are active, but the secondary is hidden behind a shadow. So it will not sense the primary, but then if it starts transmitting, it can still interfere with the primary receiver, which is in its vicinity, but outside the shadow and able to actually have an active communication with the primary users. And so one actually likes to do, or it is preferable to do cooperative spectrum sensing, where these secondary nodes cooperate with each other in order to figure out which frequency bands are occupied. And in that case, each secondary user is taking measurements of the entire wideband signal, and they need to kind of exchange this information. For example, they could, if there is a centralized controller, they could all send their measurements to a centralized controller, which will then solve a simultaneous sparse or joint sparse recovery problem to determine which frequency bands are occupied. And again, this is a problem of support recovery. You don't really need to recover the actual signal being transmitted by the primary user. And if you can reduce the number of measurements, you can reduce the communication overhead and latency of the communication between the secondary users with each other, or between the secondary users and a centralized controller, which is solving this multiple sparse Bayesian learning algorithm. Does that answer your question?
Shall we use other techniques, so OMP, other techniques are there?
I can't hear you very well. Can you speak up, please?
Sir, already we are using OMP, optical and passive techniques are there for sensing.
Hmm.
But what is the special of this joint sparse?
Well, okay, so first of all, OMP by itself is an algorithm for recovering a single sparse vector. The joint sparsity arises only when you get multiple measurements. So I have to go to, instead of looking at single measurements, I need to go to models like this, where you get multiple vectors, y1 through yl. Okay, and when you have multiple measurements like this, then you have to extend this OMP algorithm if you want to exploit any joint sparsity structure. Yeah, and if you do exploit joint sparsity structure, that's like additional structure in the signal. So you see these signals here, this matrix X, you see that there's a lot of structure in it. Not only is each column of X sparse, the locations of the non-zero entries are common across all the sparse vectors. Right? If you exploit that extra structure by the joint sparse recovery algorithms can recover the support of these sparse vectors using much fewer number of measurements. So I think maybe I didn't emphasize this enough, but the name of the game here is how many measurements do you need in order to correctly identify the support of these vectors? And what is the trade-off between the number of measurements per vector and the number of measurements you are getting? So the number of measurements per vector is m, and the number of vectors you are measuring, observing is L. So what is the trade-off between M and L? Should you use a larger value of M and a smaller value of L, or should you use a smaller value of m and a larger value of L. And this in turn depends on the kind of problem you're looking at. If it is feasible to take more number of measurements per vector, then of course you can try to increase m itself, and then you don't even need multiple measurement vectors, and you don't need all this joint sparse recovery framework. But in other problems, it's possible that the having more number of measurements is easy. That is, increasing L is easy, but taking more number of measurements per vector is very expensive. In that case, you want to take as few measurements as possible per vector and still be able to recover either these sparse vectors or their support, depending on what you're interested in. Um, and it's possible that you can get a larger number of vectors. So L can be large, but M needs to be as small as possible. So depending on the scenario or the problem application that you're considering, either M or L could be more important to optimize. But if you do exploit this extra structure, MSBL can give you far better performance than simultaneous orthogonal matching pursuit. Just like SBL can far outperform orthogonal matching pursuit. So generally, I suppose one important message of this tutorial is that if you're interested in sparse signal recovery, in this day and age, you really need to look beyond L1 optimization or L1 minimization or orthogonal matching pursuit. Those are the algorithms of the early 2000s. There are much, much better algorithms that are available today, and one really shouldn't be looking at those algorithms.
Can you tell me any materials, sir, to read the recent algorithms?
About which? About what?
About this joint sparse recovery and also this advanced algorithms.
There's a lot of material, but I have some references at the end of my presentation, which maybe I can share the slides with you guys after the talk. But these are some of the references. So this 1, 2, 3, 4, the fourth reference here. Okay, that is one of the early papers that discussed about the MSBL algorithm. Transactions on Signal Processing, 2007. Its title is An Empirical Bayesian Strategy for Solving the Simultaneous Sparse Approximation Problem. But there are other papers here. Any other questions? Okay, so if yeah, go ahead, please.
Sir, I just need clarification in type 2 methods. Sir, first we are we are assuming prior on X. And then again we are solving not parameterizing variance actually. In this problem.
Correct.
Then we are solving the variance.
Correct.
Again, then we are optimizing the problem, sir. Then we are solving the optimization problem after solving this hyperparameter.
Correct.
Sir, so we are going this much process in type 1. Actually, sir, what is the advantage over this type 1, sir? Some advantage.
Okay, so the main advantage is that in type 1 methods, you are effectively choosing one single prior.
Yes.
Okay, and you are trying to find the map estimate under that prior. Whereas in this type 2 method, what you're doing is you're actually using a continuum of priors, because gamma is a continuous variable. And so for every choice of gamma, you have a new prior on X, because X is distributed as Gaussian with zero mean and covariance capital gamma.
Okay.
So effectively, what this is allowing you to do is to explore a continuum of different possible priors and find the best prior that explains your observations why. And the main advantage that comes out of this is that it works much better than the previous these type 1 methods in general. And in fact, the power of SBL really comes out when you start looking at measurement matrices that are not well conditioned. That is, when the columns of phi start becoming a bit correlated, or if the columns of phi are, if it does not satisfy the restricted isometry property or things like that, then, and because in many practical applications, the matrix phi is not choosable. You cannot choose it to be, some random numbers. It's what nature gives you many times. And in that case, you have to live with whatever measurement matrix you have, but really work on which recovery algorithm gives you the best possible performance. And in those kind of scenarios, these algorithms, empirically, they have been found to work much better. And now there is actually a pretty solid understanding of the theory behind this also. Unfortunately, the theory behind why these algorithms work is something, it's quite mathematically deep, and it's actually quite difficult to present it in a tutorial style presentation. That is something that you probably have to pick up by reading some of these papers on your own.
So generally, variance can be parameterized, mean can be parameterized, or is there any other parameters that can be parameterized?
You can
Correlation.
it's also a very good question. So why is it that I'm choosing only the variance as the parameter? Why didn't I choose X to be, let's say Gaussian with mean mu and covariance gamma, and then leave both mu and gamma as parameters and so on? So it's not easy to answer that question. I mean, it's a combination of different things. But perhaps the most important consideration is, are you able to develop a tractable algorithm under your parameterized model? And it turns out that this works. And with this approach, you can develop a beautiful EM algorithm, which is conceptually very easy to understand. And it's actually very easy to implement as well. It's just that the computational complexity of the implementation is on the higher side. But for that, there are other approaches that can reduce the computational complexity, like this AMP-SBL that I discussed. There are also other, inspired by this one, there are also other priors. There's a spike and slab model and a variety of priors. There actually, the most general version is what is known as a Gaussian scale mixture model. And that Gaussian scale mixture model has a lot of these models as special cases. And under that general prior model, you can still derive a tractable algorithm. And so this is not the only choice. Part one of the answer. The part two of the answer is that you have to be a little careful in choosing these priors, because you want to develop a tractable algorithm that gives you good performance as well.
Okay, sir. Okay. Thank you, sir.
Welcome. Okay, so thanks for all the questions. But I think, it's a good idea to take a short break, because as I said, I think going continuously for 2 hours is very heavy. So it's 3:47 in my clock. Maybe we can get back together at 3:52 in 5 minutes time. Is that okay?
Yes, sir. Thank you, sir.
Okay. Yeah. We'll come back in 5 minutes. Okay, welcome back. Shall we begin? Can you hear me?
Yes, sir.
Okay. Any questions? Okay, so now I will
Sir,
talk. Yeah. Please.
sir, is sparse recovery reliable in wide spectrum sensing, sir? Because sometimes the secondary users may give the erroneous decisions, such as regarding the presence or absence of the primary user.
Right. I mean, so see the way I look at it. Let me see how. Okay. So any detection algorithm, right, is prone to error. So the question is whether sparse recovery can give you. It's all a question of a trade-off between performance, complexity,
And
and ease
accuracy.
of implementation. Okay, and so basically, so one way is, for example, you so if you are thinking of a secondary user who is very far away from a primary user, then of course the secondary user will miss the primary. But then it may not even matter, right? Because if the secondary user transmits data when it is very far away from the primary, chances are it is very far away from the primary receiver as well. Okay, so in some sense, where this whole thing gets a bit complicated to describe is that when you think about what is a spectrum whole, right? It's actually specific
The
to
absence of
the absence of
primary user
primary.
in a spectrum.
That is
In a
not it,
spectrum,
right?
sir.
Yeah, that's not it, right? Because there is also a spatial aspect. Okay, so if you think about a, think about a primary transmitter and a set of primary receivers. Okay, now there is some communication going on between the primary transmitter and this set of users. Or let's say there are a set of
Yes,
primary
sir.
transmitters and a set of primary receivers. And there are some communications going on in between them. Now, if your secondary user is sitting close to any of these primary transmitters and receivers, then it needs to sense the spectrum accurately, and that too, it only needs to sense the primary users in its vicinity. Okay, the other users who are far away, it need not care about, because even if it transmits, so for example, if there are, let's say there are there are two pairs of primary transmitter receivers. One pair is exchanging data at a frequency f1, and the other pair is exchanging data at frequency f2. And let's say these two pairs are far away from each other. If you have a secondary user close to the first pair, and if it tries to sense the spectrum and it senses that only f1 is occupied and it misses that f2 was also occupied, but then it transmits data to its own secondary receiver, because it is far away from the primary user pair which is using frequency f2, it doesn't matter. You should not think of it as an error in spectrum sensing. So actually a spectrum hole is specific to the location. At different locations of secondary users, you will have different spectrum holes,
Okay, sir.
right? And so, the point about these sparse recovery algorithms is that it helps you reduce the number of measurements you need in order to get and equally reliable sensing of the primary network. And by reducing the number of measurements you need, you can hopefully speed up the time it takes to sense the spectrum. So for example, if method A requires 100 samples to detect the primary users accurately, but if a sparse recovery algorithm, by exploiting the underlying sparsity, only needs 10 measurements, then potentially you can sense the spectrum in 1/10 of the time that another non-sparse recovery based technique would require. That is one way to think about it.
Okay, sir. Thank you, sir.
Yeah. There is a paper titled What is a Spectrum Hole and What Does It Take to Identify It, or something like that. And the author is Professor Anand Sahai at UC Berkeley. It's a beautifully written paper. You can look at that a bit to get a feel for what I'm referring to here, which talks about the spatial aspect of spectrum holes.
Spectrum. Thank you, sir.
Welcome. Okay, so now let's discuss briefly about some applications of the sparse Bayesian learning idea in channel estimation and data detection applications. Given that we have only half an hour, what I'll do is to actually focus on the big picture and show you some performance graphs, which kind of bring out the advantage of exploiting sparsity in these channel estimation and data detection problems. So again, this is a slide I showed you earlier, which basically makes the point that wireless channels are exhibit multipath, which makes them naturally sparse in the lag domain. And one can try to utilize this lag domain sparsity of the channel for channel estimation, followed by channel equalization and data detection. So there are different models one can use for these wireless channels, popular ones being block fading channels, where the channel remains constant for the duration of a block and then changes in an independent and identically distributed manner from one block to the next block. The other case is where you have a time varying channel. So channel varies from symbol to symbol. And in this case, if the channel varies from symbol to symbol, the channels are temporally correlated. And this one can actually utilize this temporal correlation or exploit this temporal correlation to improve the channel estimation performance. Yeah, this basically shows a block diagram of how the channel estimation works. In a typical OFDM system, you mount data on different subcarriers. And on some subcarriers, you may mount pilots, and other subcarriers, you may mount data symbols. But then one can potentially, or one typically utilizes the subcarriers that are mounted with pilot symbols to perform channel estimation, followed by data detection of the subcarrier, which are mounted on subcarriers carrying data. And one possibility that we have explored in this work is, if you can detect the data symbols, you can potentially reinsert the data symbols back into this picture here. So you replace the question marks with your detected data symbols. And now you have more number of pilot symbols, and you can potentially use that to improve your channel estimates. The channel is this vector H here, and you can improve your channel estimates and then go back and detect the data symbols again. And that can potentially improve the performance. And so if you look at this particular type of system and cast it into a sparse recovery framework, because you're trying to estimate the channel in the lag domain. And so this time domain or lag domain channel H is an L length vector which has only a few non-zero entries, because although the delay spread of the channel is large, it doesn't have that many number of non-zero components. Then you can exploit this sparsity to estimate this channel. And you can cast this channel estimation problem exactly in this sparse Bayesian learning framework and develop an E step and M step. And like I mentioned, you can actually do iterative channel estimation and data detection. And it turns out that the E step splits as two separate E steps, one for updating this gamma and the other for updating the estimates of this data symbols X on the data subcarriers. And if you do that, and here's a simulation result of the mean squared error in channel estimation. So this considers an Ofdm system with 256 subcarriers. The maximum delay spread of the channel is taken to be 64, but it is a pedestrian B power delay profile, which is one of the 3GPP specified channel models, which has 6 non-zero taps. Then we transmit 7 symbols per slot, and there are 44 pilot subcarriers, and so 256 minus 44 is the number of data subcarriers. And the data is transmitted using quadrature phase shift keying with a rate half turbo code. What is plotted here is the mean squared error in channel estimation as a function of the signal to noise ratio. There are a lot of curves here, but maybe I'll just call your attention to 2 of the curves. Or to a few of the curves. First of all, the diamond curve, which is marked CS, is the mean squared error you will achieve by using a conventional sparse recovery algorithm like L1 recovery. If you directly use this sparse Bayesian learning using the 44 pilot subcarriers to estimate the channel, you will get the pink circle curve. So you can improve performance quite a bit, and in fact, the CS curve is flat, is saturating with SNR. The mean squared error is saturating with SNR, whereas the SBL algorithm has a mean squared error which continues to linearly decrease with the SNR up until 30 dB of SNR. But what is even more interesting is the green square and the pentagram, whatever, brown color curve, which is the ones marked JSBL and RJSBL. They're actually the same algorithm, but RJSBL is a faster version of JSBL. But this does this joint sparse Bayesian learning where it's jointly estimating the data and the pilot symbol. So it's iterating between estimating the data and then followed by re-estimating the channel, and then going back and re-estimating the data symbols, and using the new data symbols, going back and re-estimating the channel, etc. And you can see there is a huge, like almost 2 orders of magnitude improvement in the mean squared error when you use this kind of joint processing. And in fact, it outperforms an algorithm which is optimal, an optimal Gini-aided algorithm which knows the locations of the 6 non-zero taps. So that is the MIP. It is aware of the multipath intensity profile or the power delay profile, but uses only the pilot symbols to estimate the channel. Because the joint SPL algorithm at some point is able to recover the support correctly, it's as if it actually knows the support, and then it is using all the data subcarriers and the pilot subcarriers to estimate the channel. So it's able to actually achieve much better performance than even Gini-aided channel estimator, which is aware of the locations of the non-zero taps. This is another example which basically shows the bit error rate plot as a function of the SNR for the same set of algorithms that I presented in the previous slide. My main reason for including this in the presentation is to show you the performance of uncoded versus coded transmissions. And what you will see here is that this MIP aware pilot only, and if you look at that curve versus this JSBL, if you look at the uncoded case, which is a solid curve, so if you compare the green curve to the black curve, the green curve is below the black curve, meaning that you can have lower bit error rate by using this RJSBL algorithm compared to using the MIP aware pilot only. That's a Gini-aided approach. It's not practical, but the RJSBL is able to beat the MIP aware pilot only curve. But when you go to the coded case, you can see that the MIP aware pilot only is actually much better than this joint SBL, the green curve, right? And so the reason I point this out is because most practical communication systems these days are coded communication systems. And so when you're looking at performance of different channel estimation and data detection techniques, it's not just the hard data detections that matter. In fact, it's important to come up with good estimates of the soft symbols or the bit log likelihood ratios. And that actually ultimately determines the coded system performance of these schemes. So you will find tons and tons of papers which show performance improvement in terms of BER when it comes to uncoded transmissions. But if you ask them to generate the performance under coded communications, many of those techniques will totally fail. It isn't really the benefits that you observe in uncoded transmission don't translate to benefits in the coded communication case. And so it is important to look at both. That's the only reason I brought this in here. So if you're trying to do research, please keep in mind that showing performance results for uncoded communications is often not enough. You should look at the coded case also. The story may be completely different in the coded case. Okay, now coming to time varying channels. Like I mentioned, if the channel is time varying, the channel is correlated from symbol to symbol. A popular model is that of the autoregressive model, where the channel at time k is written as rho times the channel at time k minus 1 plus an innovation term uk. And this factor rho depends on the normalized Doppler frequency, and this is also known as it is obtained from something known as the Jake spectrum. And so this is a very well accepted model in the wireless communications literature. And this SVL framework can be extended to incorporate this temporal correlation. In fact, when you see this kind of AR models, the natural approach to consider is to use a Kalman filtering framework to estimate the channels, which basically will allow you to account for all the past symbols, all the past observations to come up with the best possible estimate of the channel at the current time index. And that is what we did in this work, which is to integrate the SBL framework into a Kalman filtering framework to obtain a joint Kalman SBL, which basically involves the 3 Kalman steps, which is the prediction, update, and smoothing steps. And that is alternated with the M step, which is the same as what I showed you earlier. And this basically gives you a low complexity implementation of the joint sparse recovery, but one which also exploits the temporal correlation of the channel. And again, this is some simulation results which show the performance of these algorithms. Now, since we are discussing this Kalman SPL, you should focus on the curve which is labeled JK SPL, which is the green curve. And you can see that that has the lowest, the best mean squared error performance from the left plot. In fact, it is only slightly worse than the MIP aware Kalman, which is basically a Kalman filtering where the support of the sparse vectors is exactly known. So that's exactly the Kalman filtering framework. And obviously that's a gene-aided setup. You can't beat that, but it comes pretty close to it. And it's better than all the other algorithms. And if you look at the plot on the right, it sort of tells a similar story, but in terms of the BER versus SNR. And once again, there is a comparison of performances in both the coded and the uncoded case. And as you can see in the uncoded case, the Kalman SBL or the JK SBL curve is pretty much overlapping with the gene-aided curve, which has perfect channel state information. But even in the coded case, it only has a small loss in performance compared to the gene-aided case. So in this case, the JK SPL actually loses very little by going from the uncoded case to the coded case. Now, the next extension is to the case of multiple antenna systems. So we'll now look at Mimo OFDM systems. And as I mentioned, in the case of Mimo, what happens is that although there are different channels between every pair of antennas, so you can see this in the equation at the bottom there, you have H, NT, NR. So depending on the transmit and receive antenna index, you have a different lag domain or a channel impulse response. For each pair of transmit receive antennas, you have a different channel impulse response. But this channel impulse response between different pairs typically has the same support, although the non-zero coefficients will be different. And so this is exactly the same framework as in the joint sparse recovery framework that I described to you earlier. So you can take this XNTF as an overall measurement matrix, but XNT itself contains both pilot and data symbols are unknown. So you'll need to do this kind of a alternating optimization where you estimate the channels, then you follow it up with trying to detect the data, then you substitute the data into this XNT, go back and estimate channels, etc. But and also simultaneously exploit the joint sparsity of this HNR NTNR across different values of NTNR. So that can be done, and there are some details in these slides. Basically, you can see that this overall, it's written here in the top box there. You have a set of measurements Y, which can be written as a measurement matrix phi times this H, which has this L and T cross NR, but with common sparsity across the different columns. And so you can exploit that joint sparsity to recover the lag domain channels with better accuracy than if you were to use the single measurement vector approach, where you take the measurements at each antenna separately and try to estimate the channel from the different transmit antennas. So this basically shows that the same E and M step that I showed you earlier can be reused for this kind of a problem. It's instead of the SBL algorithm, as I discussed earlier, it's now the MSBL algorithm. That's the only difference. And yeah, this just talks about the extra step of data detection. Effectively, this is like the sensing matrix phi is not completely known. There are some question mark fields that need to be filled out. And the approach here allows you to do this joint channel estimation and data detection, which is essentially trying to figure out these embedded parameters in the phi matrix. So if you do all of that, then you can get this kind of a performance. So if you use simultaneous OMP, which also exploits this joint sparsity structure, that is the mean squared error. That's the top curve here that performs the worst among the ones that were tested. If you use MSBL by itself, it exploits the joint sparsity, but it doesn't exploit the fact that you can detect the data symbols and reuse them as pilots. But this JMSBL is something that is actually you reusing the data symbols to obtain better channel estimates. And you can see that again, there is maybe 2 orders of magnitude improvement by going to this joint MSBL approach. The MIP aware EMOFDM and MIP aware pilot only are gene-aided channel estimators, which are plotted just for benchmarking purposes. And this plot basically tries to emphasize the point that exploiting this joint sparse structure helps, because you can see the comparison between SPL, which does antenna pair by antenna pair channel estimation, versus the MSPL, which exploits this joint sparsity structure, and both with joint channel estimation and data detection, as well as standalone channel estimation, which are the purple curves. You can see there is a considerable improvement, almost 1 order of magnitude improvement in the mean squared error that you can achieve. This, this is a reiteration of the same point, but in terms of the BER performance. So I'll just go ahead. Many other applications, like multi-user beamforming, in the millimeter wave, autonomous cars, and detection of multiple targets, spectrum cartography, which talks about the problem of mapping the spectrum usage over time and space, and spectrum whole search, for example, in cognitive radio applications, etc. And there's a lot of papers that you can find on the use of sparse signal recovery in many communications problems. But I suppose the point of my presentation is that there are Bayesian methods which have simple updates and very promising performance. There are interesting challenges related to the theoretical analysis of these algorithms, developing newer and faster versions of these algorithms, and also looking at novel applications where one can use these algorithms to obtain better performance or do something that couldn't be done with the previously known algorithms. So overall, I would say that these Bayesian methods provide plenty of opportunities for interesting research in this area. So I'm a little ahead of time. I can go on and cover other things also, but I suppose it really depends on you if you want to hear more things. These are some references. Like I said, I'll try and share the slides with you later. And I'd like to acknowledge 4 of the key students who contributed to a lot of the material I showed you today. Gitu Joseph is one of my recent PhD graduates, and she's currently a faculty at TU Delft in the Netherlands. Saurabh Khanna got his PhD a few years ago, and he's currently a faculty at IIT Roorkee. Ranjita Prasad was one of the early people to work on sparse signal recovery related algorithms with me, and she's currently a faculty at IIIT Delhi. And Vinutna did her master's with me, and she's currently working at Qualcomm. I'd acknowledge their help in all of this. Research work doesn't happen without the help of really bright students, and these are some of them. That's the end of my presentation. Thank you very much. I'm happy to take any final questions. Okay, I think there aren't any questions. It's been a long day for all of you, so I thank you for your time and patience. All the very best. Enjoy the rest of the workshop.
Thank you.
Welcome. Okay, so I will sign out now. Thank you very much.
Thank you so much, sir, for your patience in delivering the 4 hours lecture, sir. Thank you so much for accepting the invitation from MIT Andhra Pradesh, sir. In future also, in future also, if your voice is not audible.
Oh yeah, I didn't, not unmuted, but I'd be very happy to hear feedback from the audience, especially feedback of constructive nature and what could have been delivered better, or what you would have liked to see more of. If you could please share it with Dr. Kishore Kumar, and
yes,
you can maybe pass it on to him.
Yes, sir.
Thank you.
Thank you so much, sir. Thank you so much. So as a token of appreciation, I request all the participants to turn on your mics and give a big round of applause from my side. Thanks a lot, sir. In future also, if any such workshops are being planned at NIT Andhra, we may request you, sir. Thank you one and all for being over here. So tomorrow is the last day for our faculty development program, and tomorrow on IIIT Hyderabad, Dr. Santosh Nanmodi sir will be taking the sessions, 2 hours, total 2 sessions he will be taking on DOI estimation based on sparse compressive sensing.